is an assistant professor of civil and environmental engineering at the University of South Carolina. Her research interests are on the development and application of mathematical models for fluid flow, pathogen dispersion, and decontamination in the environmental system, with the objective of informing risk assessors and first responders. Professor Hoque's recent studies have involved multi-physics modeling that applies computational fluid dynamics analysis and neural networks to predict bioaerosol transport and inactivation in indoor areas. Professor Hoque's work to model COVID-19 transmission was featured in her area's local news from early in the pandemic. Dr. Hoque received a PhD in environmental engineering from Drexel University under one of our other speakers, Chuck Haas, a Master's of Applied Science in Chemical Engineering from the University of Toronto, and a BSc in Chemical Engineering from Bangladesh University of Engineering and Technology. Please welcome Professor Hoque to speak with us about the influence of surface characteristics and flow dynamics on SARS-CoV-2 transmission.
Thank you very much for that introduction, Amy. And good morning and good afternoon to everyone who's watching from wherever you are. This is a collaborative work across the field with professors at Department of Chemistry and Biochemistry at USC and with collaboration with Ohio State and Michigan State University. Next slide, please. So we have heard about aerosol transmission and about its release in the atmosphere, in the bulk air, and in our indoor spaces. I'm going to actually focus on how we can take those decisions so that we can actually build spaces which are safe and healthy for us. A virus, which as we just heard, once it's released in a droplet or in something inside, it's never released on its own. Once it's released, it will travel in the bulk air and find its way somehow or the other to the surface. In the middle of it, there would be the boundary layer which demarcates between the bulk air and the surface. Once it reaches the surface, it will interact with that surface depending on the properties, and subsequently it may remain attached or depending on maybe activities which could cause it to resuspend back into the bulk air. Next slide, please. So first, we're going to take a look at what happens if there is an interaction with viruses and surfaces. And these experiments were conducted using a vaccinia virus, and the intent is to move on to lentivirus, which is a model for SARS-CoV-2. And this work has been funded by the USC Emergency COVID-19 Fund. We looked at what would happen if we passed vaccinia virus and allowed it to deposit on different kinds of sensors using a very sensitive microbalance, the QCMD approach. And subsequently, we tried to find out what would happen if we tried to wash out that virus using different flow rates. Next slide, please. So the experiments was done with multiple surfaces, and we have here glass, silica, gold, and stainless steel. We are continuing our experiments with copper surfaces, as well as with measles virus. Current results have shown us that stainless steel stands out when it comes to having a high mass adsorption onto the surface. And then when we subsequently try to wash it off, we have stainless steel, which actually holds on to the virus, as opposed to glass, which allows the most washout, followed by silica, gold. And atomic force microscopy has shown that this is mainly due to surface charges, both belonging to the virus as well as the stainless steel. So what this kind of tells us that as we go through and try to understand how this transmission happens in our environments, we can look at these different surface properties and see how they interact. And this gives us an idea of what to choose when we go ahead and try to design or inform the materials we use in our day-to-day life in our built spaces. Particularly, please go to the next slide. Particularly if we now focus on bulk airflow. So currently this picture that we just had looked at disk shields, right? Currently all our children are going to schools and we have disk shields as one of the protective measures. So the question that might come about is, are those disk shields effective, and what would make them more effective, or whether or not we need to think about materials or where they're located. Next slide. So these are computational fluid dynamics simulations, which try to look at detailed airflow modeling on where the air travels and where particle travels. I have one disk shield and two sources of sneeze, one at a child's breathing level and the other at an adult's breathing level. The second plot shows actually a plot of velocity magnitude at different locations in that room. And while we have low velocities across the room, if you notice, just behind where the disk shield is located, there is a slightly higher velocity compared to the rest of it, which indicates that which was not there when the shield was absent, which indicates that the presence of the shield immediately makes an changes or disrupts the pattern in which the air flows into that room. Next slide, please. So we assessed what would happen if airflow and sneeze direction were altered. So the red arrow indicates that the airflow is in the room is in the opposite direction to the sneeze. The black arrow indicates that the sneeze is in the direction of the airflow. So if you look at the two plots at the top, which is red bordered margins, where we have the flow of the sneeze in the opposite direction to the airflow, incorporating a partition reduces the time of exposure, the total number of particles inside the room, from around 8% to 3%. The green line is when the sneeze occurs from the adult, and the purple line is when the sneeze occurs from the child. Now, if we go down to the plots below those two, where we have the black line, which is the sneeze is occurring in the direction of the flow, you will notice that the presence of the partition actually causes more particles to stay inside the room, as opposed to when there is no partition. And the case gets worse for the child who's sneezing and who has the shield in front of him or her. So it goes from nearly 0.02% to around 4.3% remaining after around 15 minutes. Next slide, please. So we focused at the worst case scenario to take a look at what's happening to the particles overall and tracked their changes over a 15-minute period. And without the partition, if you notice, that's the second plot, most of the particles have already moved away after 1 minute, which has not happened in the case for the first when we have the partition. So this reinforces the fact that we have to take into consideration not only the fact that someone is sneezing, but also when we make design choices, what the airflow conditions are within the room. That way we can make an informed decision on designing so that we actually consider the fact that airflow would influence the pattern in the room would be influenced due to the way we have designed our indoor spaces. The surfaces also, if we have the disk shield made in certain surfaces, we could learn more about how different materials would influence that interaction with those droplets which are being released and possibly interacting with the surfaces. Next slide, please. So finally, I just want to focus once more that this particular pandemic has highlighted how much multiple disciplines must come together and work together. This particular slides I put together involved fluid dynamics, aerosol physics, and surface chemistry, and needed input from multiple disciplines. It's not a one-size-fits-all approach. We have to be open to the fact that multiple designs we have to look at different ways that things could actually make changes. Solutions do not have to be expensive. We just have to figure out how we have to make that solution with our information that we can get from our research, which can actually transform how we design buildings. And this can also lead to us learning how to actually design safe, healthy, and affordable buildings that can support equity in design and construction. Thank you.